Okay, first of all, hello everyone. I'm Çağatay Kırmızıay. I'm a master's degree student at İzmir University of Economics. And also I'm a research assistant in this university and at same department. My supervisor is Assistant Professor Mehmet Türkan. We are working on the image denoising problem through the neighbor embedding. Today I'm going to talk about this problem, image denoising problem, with the brief explanation of our method, our approach. But first of all, let's start with the brief history of the image denoising. Actually, image denoising problem is it's not new problem. The researchers have worked on over many years, like 50 or 40 years, but still is a problem with the developing technology, all the developing technology, and there are many factors can affect the image quality, like natural factors, environmental factors, and the human-made factors. And because of these factors, before the analysis of the images, we should get rid of the unwanted or noisy parts of the image. That's why we are working on the image processing, and we are creating an estimation process for the noise-free image, and it's really hard because of the unknown parameters. And of course, if you check the brief history of the image denoising problems, there are some benchmark articles, benchmark methods about the image denoising. The first one is, I think, the BM3D. Konstantin Dabov and his team published several articles about that, and it's very famous, and it's very high quality algorithm for the image denoising. And they are using the patches, selecting by a reference patch, then select the patches similar to the reference one. They are collecting them into stack, and they're applying a collaborative filtering into the stack. Actually, the main points, I'm not gonna deep inside the theory of some benchmark articles, but I want to emphasize some critical points about the methods. The BM3D is they are using the image patches actually, and collaborative filtering, and they can even change the shape of the patches by applying a PCA. They are extracting the principal components of the patches, and also they can apply this BM3D method on colored images. And another method is the Michael Elad and the Michel Ahoran's study. They are using the dictionary learning from noisy image patches, and they accept that the standard deviation of the noise is known parameter, and they are creating an optimization problem to estimate the noise-free image. And you can see the basic example of the mathematical approach. And if you see my mouse here, this part of the equation is representing the patch size. They are calculating the weights actually here from the patch size patch approach, and they are creating a noise-free estimation of the patches by applying an optimization problem here. So, and the other one is the multi-resolution bilateral filtering. Actually, this bilateral filtering is very similar to Boades non-local mean filter. If you check these two methods, you can see that if the patch size of the non-local mean filter is equal to 1, then we can call that it's a bilateral filter. And the critical point is about this article here, multi-resolution bilateral filtering for image denoising, is there are penalty terms about the intensity difference and the spatial difference about the pixels. You can see that decaying exponential functions here, and they are using these terms as the penalty terms. And of course, this method they are using pixel values just itself, but they are using a neighborhood pixels here. And you can see that the multi-scale application, it's important because by using that you can change the frequency behavior actually, but it's not important for us now. The other one actually, as I mentioned before, non-local means algorithm of Boades, it's very common and well-known algorithm. As I said before, they are using exponential decaying exponential terms for penalty about the intensity and the special, and this method also use the patches here. The other one is the weighted nuclear norm minimization with application. As you can see here, they are using the overlapping patches. They are collecting into a stack by creating a nuclear norm matrix of the patches, and they are calculating the weight for each stack. Then they are reconstruct the noise-free image by iteratively, and you can see the basic algorithm of that. The critical point about the weighted nuclear norm minimization is here. The patch sizes are changing. Actually, they are changing because of the depending on the noise standard deviation and the neighborhood numbers that we use for the application. And then let's focus our approach here. We are using a locally linear embedding method, and it's not a common thing for the image denoising problem, but we are trying to use the locally linear embedding. Actually, LLE, locally linear embedding, is a dimensional reduction method here. As you can see here, there is an example about that. This data is a Swiss roll data, and you can actually dimensional reduction. You can apply dimensional reduction method for this data by using different algorithms like PCA. As you can see here, PCA result is shown here. But PCA does not preserve the data geometry, and by using the LLE you can preserve the data geometry, as you can see here. But in this case we are not using the actually the, how can I say, the dimensional reduction approach. We are trying to reconstruction method because the algorithm is very basic. Let's assume that we have a data here, and by using the neighborhoods data, actually the data can be pixel or can be patch in the image sense. So we are representing the this data by using the neighborhoods relationship, linear relationship between the data points here, and we can mapping into low dimensional space by using these weights actually. So that's why we are creating different versions. We are going to the step by step actually. The first step of the our study is extracting a search window. So as you can see here, this figure shows that there is a noisy image here, and we can extract search window for each pixel of the noisy image. If it is needed, of course padding should be done, as you can see here. So after the extraction of the search window, now we are trying to patch size applications inside the search window. Of course, we have a reference pixel at the center of the search window and the reference patch here. And the search window size actually is depending on the patch size here. Let's assume that we have a patch size 5 by 5, then the search window size should be 15 by 15, 3 times of the patch size, let's say. Then we are applying sliding and the overlapping patches demonstration inside the search window. Then we are collecting into a matrix, and each column of the A matrix is representing one patch. Actually, we are converting into column vectors here. But in the first version, we are using the all patches inside the search window except the reference patch. Then we are calculating the locally linear embedding weight. Then by using these weights and the A matrix, we can get the estimated version of the reference patch actually. But we are not using the whole reference patch values here. By actually extract the value for the estimation of the reference pixel, and we are putting in the right place of the reference pixel. And we are not replacing the patches, we are replacing the pixel values here. So we are using the set12 dataset for the testing, and you can see the very popular examples here. The first one is cameraman, the second one is house, and the third one is the Lena. And I will show the cameraman example first of all. These graphs show the PSNR and the SSIM performance about the cameraman image, and we have, as you can see here, 14 different noise levels by using, we defined by using the noise standard deviation here. And actually in the version 1, we want to reveal the relationship between the patch size effect on the image reconstruction. As you can see, we have the patch size 5, 9, 13, and the 15. The 0 one represents the PSNR value between the noisy one and the original one. The other ones between the estimated one and the original one. So as you can see that the PSNR value actually values are changing depending on the patch sizes here, and also SSIM values are changing. But we can say that the first one for the cameraman pixel, the suitable one patch size is 5. But if we check the second image here, the second image is house, you can see that we have to apply different size of patch. So actually this shows that, and also let's check the Lena, for example. You can see that the relationship between the noise levels, patch size, and the image content. So we can say that the suitable optimum patch size is changing depending on the image content and the noise standard deviation actually. So if you see that this result of the version 1, you can easily see that actually we are not getting rid of the noisy parts of the image, just we are using the reconstruction process of the LLE. And I just want to show the patch size effect here. If you focus on the arm part of the cameraman, you can really see the blurred parts of the images. So then we will move on to version 2. Actually, the main aim is to reduce the number of the atoms in the A. It means that use less patch for the A. So we actually created the weighting algorithm for the patches selection. We use the differences between the patches. Actually, we apply the similarity for the patches, and we use the penalty term like a exponential decaying factor. Then we actually set the threshold lower limit with some different multiplier values, and we want to reveal the relationship between these how can I say, threshold limiting multiplier and the results. And you can see the basic algorithm here. So we are now doing this, and again actually I shared a table about that. On the left hand side you can see the noise standard deviations and the PSNR value between the noisy one and the original one, version 1 results, and the blue columns are representing the version 2 results. As you can see that we are using the different values for the thresholding multipliers, and actually there is no very huge improvement about the PSNR values, like and these are actually these are same, because these, it means that these thresholding multiplier cannot eliminate any patch because of the similar. So actually we discovered that the weights of the patches are similar, very close to each other. So that's why we need to use higher multiplier for the thresholding values. And there is a little improvement, and I think it's promising, because we have just done the reconstruction process. We don't even include the denoising problem here, denoising optimization problem here. So, and also SSIM results, but for the time, let's skip that. And then we improve the version 3. Again, the main target is the same, get the smaller version of the A, but instead of the how can I say, weighting process depending on the similarity between the patches, we are using the PCA, principal component analysis of the patches of the A matrix. then we use the dimension reduction application here, and the reduced dimension size is depending on the page size. For example, if the page size is 5, then end of this application, small a process, we will get 5 items in the A matrix. And again, the other procedure is the same. We are calculating the LLE weights and we are getting the estimated reference patch. Then we will put the estimated value of the reference pixel. And I know this is a very crowded table, but actually it's good to see the different parameters to reveal the relationship between the parameters. You can see that the version 2 results here, and the orange ones are the version 3 results. Again, we are using different multipliers for the thresholding about the weighting of the patches after the PCA. Then actually these are 2P, you can see that 2P and the 3P, these are representing the reduced dimension size. For example, in this case, if the page size is 5, reduced dimension size is 5. But in this case, reduced dimension is 2 page size, then it should be 10 and 15, it continues like that. So actually we can skip all these multipliers because of the weight values close to these values are close to each other. Then we are focusing on these parameters here, and we can say that actually increasing the reduced dimension size is not effective for all images. We can use these columns, these parameters for the computational cost actually. And actually,
could you limit your time because we have limited time. Just
yeah, it's about to finish.
Yeah, thank you.
And then we want to reveal the patch size relationship between the version 2. Actually, we are using the version 3 here, and we are using the again version 3, but the page size are different. You can see that the PSNR values of the page sizes about the multipliers. Then as for the some images, in this case you are just using actually see the cameraman result, but if you analyze the other photos, you can see that actually the page size and the multiplier can be changed according to the image content. Now we are working on the version 4 ongoing study. We are trying to get the optimization equation by using the local noise estimation. Maybe then we create a version 5 for the multi-scale application. Then we can produce a very robust denoising algorithm for any conditions. Actually, this is my end of the talk. Thank you for listening to me. If you have any questions, I will be happy to